Hello everyone, my name is Arun and welcome to my channel. In this video, it's going to be more of a demonstration video, and in this video, I'm going to show you guys how to write your own model using Fortran programming language. And for the demonstration, I'm going to use the shallow water equation model. So, the outline of this video is as follows. I'm just going to tell you the objective, and then I'm going to show you the equations involved, the prerequisites that you might need before you start this, the software required, the numerical methods used. I'm going to show you the two simple case studies after you write the model, and then I'm going to tell you the future aspects as to how you can improve this model and start with that. Okay, so the main objective of this video is to write a model to simulate the shallow water equations. Okay, I'm going to use what you call as a modular approach, wherein instead of writing the entire model in one file, one program and making it complicated, I'm going to write this in modular form, wherein I'm going to create separate files, and each file will have an important component in it, thereby splitting the work as modules. This kind of an architecture of writing a program, writing an application is very easy because you can scale it up, and if you have a very complex application or a very complex model to write, this modular structure is very easy and can be implemented in multiple other compiled programming languages as well. Okay, and this video is more of a strong programming exercise to meet realistic needs. Some people out there might have a research condition or a situation where they have to write their own model for some scientific research or some simulations or for some test applications or some whatnot. So this is going to be more of targeting those people who want to write their own models but do not know or are a little bit hesitant as to how to start. Okay, this is going to be a good exercise in that regard. So if you're like someone who wants to write your own simulations, this could be used as an example for you to start working on it. Alright, so these are the equation sets. The first one, these are the three shallow water equations. The first equation is actually your what you call as the momentum the continuity equation simplified for the two-dimensional case. The second equation is your horizontal momentum equation, your x momentum equation, and then the third one is actually your y momentum equations. Okay, this is in the x direction and this is in the y direction. Okay, and if you want to know more in detail, there is this web page. There is this Wikipedia article over here regarding the shallow water equations. There's an entire the explanation for how it has come up, and all of this is given over here. Just to give you a short overview, if you take the Navier-Stokes equation, which are actually used for looking at calculating making the momentum balance and try to simulate the fluid flow, okay, you take those equations, and then if you do what you call as a depth integration, that is assuming that the height of the fluid column does not vary significantly, and then if you say that the length and breadth of the fluid column is longer when compared to the height of the fluid column, something like yours, a very large swimming pool or a small lake or something, wherein the depth is small when compared to the length and breadth of it, like that. If you put those considerations and simplify the equations, Navier-Stokes equation, you will get the shallow water equations. So these are the shallow water equations that we are going to follow. This here, the non-conservative form, because it does not work in some cases like shocks or hydraulic jumps. Don't worry, we're not going to go into that. Okay, the terms here are as follows. U is the velocity in x direction and v is the velocity in the y direction. Okay, so since this is more related to geophysical fluid dynamics or fluid dynamics related to the flow of motions regarding on planets on a planetary level scale or simplified form of that, sometimes you call it as zonal velocity as well as meridional velocity. And h is actually the deviation of the horizontal fluid level. Okay, there is actually constant height level, fluid level, and from which the perturbations are called as small h. So we are going to give this term called as eta, which is going to be the sum of the mean height plus the perturbations height, whereas g is your gravitational constant, f is your Coriolis coefficient, v is actually a viscous drag coefficient, and mu is actually kinematic viscosity. So depending upon which fluid you take, you can vary these and then make it generic. So of course there is a much more simplified condition wherein if you neglect many of these terms, you can come up with a much more simplified equations, but this is more of a practically challenging application, so I thought I'll take this out and work it out. Alright, so these are the equations in full glory. The prerequisites you require is that you have to have some familiarity with Fortran or C. I'm going to write this model in Fortran, but if you know C, and you've already worked with if you see this video, you'll be able to reproduce this in C without much of a problem. And it's also required to for you to know some basics of making Makefiles. And if you don't know, I already have a playlist on Fortran and Makefiles. You can have a look at that. And then optionally, you need to have a little bit of idea, some knowledge in working with NetCDF files or any data file format for that matter. Okay, I'm going to use NetCDF files. You can use any data file, not a problem. And this is recommended for people who have watched my Fortran playlist, okay, and want to get to do something a little more serious. Okay, so the software required are as follows. You definitely need a Fortran compiler. I'm going to use the GNU Fortran or G-Fortran. You can use any Fortran compiler of your choice. Likewise, you need a Makefile. You need a Makefile program. You need NetCDF libraries. You can get any of them. If you're using some other data formats, you can do that. You can take it that as well. Not a problem. Definitely, you need a text editor, a terminal, and one visualizing software or a program like Python, MATLAB, R, Panoply, NCView, so on and so forth. There are plenty of them available. You just need one visualizing software to look at the results. And then I'm going to use the finite difference methods, especially central difference schemes, to write the code. And then I'm going to use the Runge-Kutta fourth order scheme to integrate these equations over time. And then I'm going to use what you call as a two-dimensional unstaggered grid for my computation. There is something called as a staggered grid and unstaggered grid configuration. I'm going to use the unstaggered one because it's much more simpler. Okay, of course, if you know this method, if you're confident with this, you'll be able to push this to unstaggered methods as well. And I'm going to use simple case studies, two simple case studies. In one case study wherein I'm going to keep the rotation to be very minimal and see how the solutions evolve. In another case, I'm going to keep the rotation significantly higher and try to see how this affects the equations. All right. And then as far as the future aspects of the model to be improved, these are the things to be noted. After writing the model, you will notice that you can write what you call as a name list file to prevent recompilation. And you can also, once you got this model running, you can actually do this and expand the model, make it much more scalable using adding OpenMP or MPI procedures inside it, making this in parallel programming, making it parallelly runnable in multiple supercomputers of that sort. And also, you can also write this in some other models of your choice. So these are some things that you can do and try this out. Okay, so with all that being said, let's actually begin. Okay, all right, so this is the folder I have. Okay, these are the equations, the presentation, these are the presentation I've written in IPython notebook, and this is the slides. Okay, so what we need is as follows. First, you need to create a folder called as src. This folder is going to contain your source files. Another one is called as objs. This is going to contain your object files. And you need another folder called as exec. This is going to contain your executable. And you need another folder called as source. What's that? Mod. This is going to contain your module files. All right. So okay, let's get started. Okay, I'm going to rename this as mods. Okay, with this being said, let's get started. First, go to the source file, and then you have to create 5 files over here. So let's create some first of them. The first file is going to be called as the initializer file .f95. This file is going to contain all your the initial conditions for the model to start with. Next, I'm going to create a main file, main.f95. This is the main program that is going to call all the subroutines and modules and run them one after the other. So this is the main central executing program, I would say. The next, let's create a parameter file parameters.f95. So this is going to contain all the initial all the value constants and variables for the model. And then the fourth one is going to be the saver module, saver.f95. This is the file that is going to have the subroutines to save the data into a NetCDF file. Okay, and finally the most important one of all, this is the core of the program. This is the core program that we're going to concentrate the significant time. This is actually your this is actually the model core, where we'll be writing the Rangikuta method and the finite difference schemes. Okay, so 5 files for each of the for 5 separate purposes. This will for the initialization of the program. This is to run the entire program one after the other. This contains the parameters and constant values and all the variables. Okay, and this contains the subroutines to save the data into and then this is the one that's going to dynamically solve the code as the program runs. Okay, so let's open up all these files. I'm going to use gedit. Where is that? Yeah, I'm going to use gedit as my text editor. You can use any editor of your choice, it doesn't matter. Alright, so let's get started with it. First, I'm going to start with the main program, and let's get on with it. So we just have to write put a comment on it. This is the main program for the model. Okay, so let's start it. Program main. Program main. Okay, and now what you have to do is we'll be using the params module, so we'll just write params. I'm going to talk about this in a moment. Use params, use model underscore vars, and I'm going to put implicit none, and then I'm going to define an integer I, and this integer is going to be our iterating variable. And now I'm just going to write a print statement so that we know what exactly is happening. So whenever this parameter module is called, it means that the parameter has been loaded. So we just parameter and variables are loaded. So loaded. Okay, let's see, loaded parameters and variables. Okay, and let's see, I'm going to call this subroutine init. We're going to write all this in one after the other. So this subroutine will make sure that all the variables are initialized. So let's print it out. Data initialized starting calculations. Okay, alright, and now what I'm going to do is I'm going to start the do loop, a time loop. Then I'm going to keep I to be varying from 2 to nt, some n number of time steps. And okay, so let's call I'm going to call a subroutine call rk4, and then I'm going to pass this variable I minus 1. So this is our this is our Rangikuta fourth order subroutine scheme that is going to run for each and every time step. So once this is done, I'm going to print this, print a line stating that calculations done for time step t equals, and then I'm going to write I minus 1 of nt minus 1. Alright, this way we know whenever it's written, whenever the program is ready, we're done with this. Okay, let me zoom this up so that it might be a little easier for you to see this. Okay, and then let me print the statement over here. So now when this entire loop is done, we know that the program is done. So let's write this out. Let's write this: all calculations done, saving data, Okay, and then then we need a module to save all of them, I mean subroutine to save all the data. So we call it data saver. This is the subroutine that's going to save all the data. And then I'm going to write print star comma all data save successfully exiting. Alright, and that's it, and that is it. This is our main program. Alright, so now this is how the structure works. The main program is going to call it the parameter module and the model was module. This module contains all the parameters required for the program to run, and this one contains all the model variables, okay, like the height, velocities u and v, and all other variables. So it's going to load them up. Then I'm going to call this initializer subroutine, which is going to set all the initial values for these variables, or the initial condition for these variables. And then we're running this do loop that is going to call the subroutine every time step and calculate the values. And then finally, when all the calculations are done, we're going to call this data saver subroutine, and which is going to take all the data and store them up. Take all the data and store them up in a particular file. All right. Now, with this main program is ready, so we can actually close this up. We won't be needing this for now. Now, with this first thing we might need is actually the parameter file. So let's go to the parameter file. So right now I've already written this program, so I'm just going to copy some of them and paste them up so that I'll tell okay, you know what, I'm going to write them as it is. So this is the parameter module for the shallow water equations. Okay, and then I'm going to write module params. Okay, and then what else do we need? We also need another module model vars and model, that will do. And then I'm going to copy down some of these variables and write them up so that it will save a bit of time. Okay, first thing what we need is the number of points that we like to put in. So I'm going to create two integer values, nx and ny. Nx specifies the number of points that we like to have in x direction, and ny specifies the number of points we like to have in my y direction, and nt specifies the number of time steps that we need. So I'm going to give it as the 10,001 time steps. Okay, and then we need dimensions and the time variables to start and end. So I'm going to write them over here. So x start indicates indicates the point, the leftmost edge of the x-axis, and x end specifies the rightmost end of the x-axis. Likewise, y start specifies the bottommost end of the y-axis, and the y end specifies the topmost end of the y-axis. Similarly, t start tells the starting time for the time variable, and t end specifies the end time. Okay. Now with these we can actually shift our geometry accordingly. So the reason why I wrote this is because if we were to have a domain that has to be asymmetric, let's say, you don't have to worry, you can directly write this in this format. And now let's get the length. So Lx is actually the length of the domain in x-axis, Ly is the length of the domain in the y-axis, LT is the total number of time, which we're going to take for the integration. And now what we're going to do is we're going to find the space stepping and the time stepping. The grid spacing along x direction, which is dx, and dx is given as Lx divided by the number of points minus 1. Since nx is actually an integer, so we have to put this float command so that we explicitly convert it to float to avoid integer division. Similarly, we get dy by dividing Ly divided by number of points minus 1, and we get the time step by dividing Lt divided by nt minus 1. Alright, and now let's define some of the constants that we'll be using in our program.
Alright, so there we go. So one of the constants we will define is the gravity, the acceleration due to gravity. I'm going to keep it as 9.8, the Earth's gravity. And then we might need pi, so I'm going to write pi as the 4 times the tan inverse of 1. So which is going to give me a very good how do I put, a very good approximation for pi up to 15 or 16 decimal places. That will be good enough for us. And then we're going to give the base height for these equations. So if you notice, shallow water equations are applicable to a water body or a fluid body, wherein the vertical height is very small when compared to the dimensional along the x and y direction. Okay, so I'm just going to keep the base height to be 1 meter. Okay, I'm going to use the SI units, I mean the metric units in all of these. So I'm going to follow with, you can follow with that. And then I'm going to give some of the parameters, the specific parameters that might be of interest. For instance, the rotation okay, I'm going to keep it as 1 e power minus 5. I'm just pressing a very small rotation over here. And then the viscous drag coefficient b that is going to come in the equation, I'm going to keep it as 1 times e power minus 3. And the viscosity of the fluid, I'm going to keep it as 1.5 times e power minus 5. I'm just going to assume this to be air. Okay, so that's the reason. And then I'm going to use 2 more constants. This will come in handy in the future. This is the perturbation, okay, and the small initial perturbation that I'm going to give for the model okay. And then this is the data file in which all the data will be saved. So I'm just going to give the data small rotation. Alright, that's it. With this, our parameter module is ready. Alright, so next thing we like to do is concentrate on the model variables. So I'm going to use params, okay, because this is going to need the variables from this parameter module. So I'm going to use params, and then as usual implicit none. How did that come along? Anyway, moving on. I keep forgetting about this. Sorry, I should have pushed this a little bigger. Anyway, I'm going to push this down. I think I don't need this for now. Anyway, then I'm going to copy these variables. I'm going to paste them up over here so you know what's happening. Alright, so these are our the x direction and y direction distances and our time variable. X is the distance along, x is the grid points along x direction, y is the grid points along y direction, and t is the time step values. And I'm going to create a 2-dimensional grid, okay, which is actually an xy grid. So it's a 2-dimensional array. So I'm going to keep it as xx and yy. Similarly, I'm going to create my variables that I'm going to be really concerned with. The horizontal velocity, meaning the velocity in x direction, which is u, velocity in y direction, which is v, and the height variation h. This is going to be eta. This is actually the eta. Since you cannot put Greek letters in programs, I'm going to keep it as h. And this is going to be the Coriolis matrix for each and every point. That is, in each and every point in the grid, we need to know the Coriolis value for this model. So I'm going to write the Coriolis matrix as f over here. Now with this, our parameter module is ready. Okay, parameter module is ready. Now we can close this out. And now let's go and talk about the initializer module. So this initializer module over here, this is going to be this is not going to be that difficult actually. This is going to initialize the entire program. So let's write it down. Module to initialize the variables for the model. Okay, so it's going to need a subroutine init, and subroutine init, and then this is also going to contain what you call as a small subroutine called as mesh grid. I'm going to write it. I'm just going to paste it down over here. Okay, so this
mesh grid 2D is going to be a very small subroutine which I found it in the internet when I was searching. If you want to generate a mesh grid values, let's say, okay, for each and every grid point you want the x direction, x coordinate and y coordinate, all you have to do is that you have to pass in the initial one-dimensional variables, the two-dimensional variables that are going to hold their sizes, and then the length or the number of dimension of these variables x and y accordingly, just like this. And this command over here, spread, it's a very handy program that's going to give you generate the coordinates for you automatically. Okay, now that being along the way, that's a minor detail. Let's go into the major stuff. So let's start with it. So we need the params modules here, and we also need the model variables over here, model underscore vars. I'm going to write implicit none, and then let's start with the iterating variables. So for this I'm going to need only a single iterating variable. Okay, just to be different from what we wrote in the main program, I'm going to keep it as I1. Okay, and let me zoom this up so that you don't curse me for making it too small. Anyway, moving along, and now let's actually fill in the dimensions, and it's going to be fairly simple and straightforward. So it's like this. You can write a do loop, or you can use a simple shorthand notation in Fortran, doesn't matter. There you go. Okay, so this will actually set a value for the grid points by an increment of dx for x, and grid points along y the increment of dy. Okay, so this is now x value, once this loop is completed, will have grid point values along from x star to xn in steps of dx. Similarly, y will have the grid point values from y star to yn in steps of dy. Alright, now once this is done, let's call in the initializer program, the mesh grid subroutine, and this is going to call this subroutine at the bottom, and it's going to generate the mesh coordinates xx and yy. With that, this part is done. And similarly, now with this done, let's actually in the same spirit, let's actually create the time variable t. Okay, so t is going to start from 0 till the end, and it's going to go from dt. So if you want, you can also write this as t start as well and proceed with it, not a problem. Alright, and now let's go for the Coriolis matrix. Now, as far as the Coriolis matrix goes by, what you can actually do is you can keep it as a constant value or something like that. Now the condition, what I'm going to do over here for my case is that I'm going to keep the Coriolis to be 0 at the set 0, okay, at the center, and I'm going to increase it sinusoidally as you approach the top and bottom. So I'm going to use this profile over here. Essentially what this profile says is that whenever y is like 0, okay, whenever y is 0, the Coriolis component is going to be 0. Okay, whenever y approaches Ly, it's going to be the Coriolis component is going to be twice the angular rotation, twice the angular velocity. So in between it will have a sinusoidal variation. Likewise, this will be same in the negative direction of y. It will have the same magnitude, but the opposite sign in the negative direction of y. Other than that, nothing much is different. You can use different profiles of your choice and then play around with it. I'm going to use a sinusoidal profile. Alright, now with this, okay, we initialize dimensions. Now I'll actually talk about some initial condition for the module. Okay, so I'm going to set the initial velocities for the program to be, initial velocities to be 0 at the initial time step, and for the remaining time steps I'm going to calculate it. And similarly for the height, everywhere else in the program I'm going to set the height to be everywhere else in the time I'm going to set this to be h0, and then what I'm going to do is that I'm just going to multiply this perturb value by this exponent of this
term over here. What this essentially gives us is that it's going to put a Gaussian well kind of profile in the beginning, indicating a small dip in the center. Okay, a small dip in the center, like something like a small dip in the height level. So once we leave this dip is going to go up and down, we're going to generate ripples, and from which we'll know how the equations respond to it. All right, so this is going to be my initial condition. This is similar to a drop of water on a pool. So if you put one drop, let's say, there will be a small dent as the drop touches the free surface. Okay, and then the free surface goes up and down. It's going to generate this equation is going to generate that, and that's it. So, and now with all of these, we have initialized our variables. Okay, with this the initialization module is done. And now before we go to the saver module, let's go to the shallow water, the main crux of this program, the shallow water, the core of this program, which is the Rangikuta fourth order scheme. Okay, so if you don't understand this, I would strongly suggest you go and read it somewhere, or look at one of my older programs wherein I have explained about Rangikuta methods in a simple manner. So this is the main solver module. Okay, and this is going to contain it's going to contain 3 subroutines. So first subroutine is subroutine RK4. It's going to take a value TS, and subroutine RK4, and then it's going to contain another subroutine called as solve and subroutine solve. Okay, and this is going to take a lot of variables, so we'll write them out as we go along. And then it's going to have another subroutine, a small subroutine called as indices, subroutine indices, Okay, we'll talk about this indices subroutine as we go along. Okay, first let's finish this RK4 module, because that's relatively easier to write. Excuse me. Now let's include the params module. We also need the model vars. I don't know why it's not picking them up. Okay, I think it's because we need the other ones as well simultaneously. So main parameter, come on. Okay, let's increase the size, and then I also need other ones, I guess. Parameter. Let's also keep the initializer module as well. I guess that way it'll help us with the auto completion. Okay, so where are we? Okay, now let's put them up. Implicit none. Alright, so first we need is an integer. Okay, and then I'm going to bring this with an intent in, and this is for the variable ts. Okay, and then we'll be creating tendencies. We're going to call them as tendencies, but they're actually not. Okay, these are going to be the intermediate slope functions for the variables u, v, and h. U1 is going to be the slope function for after the first step of calculation in Rangikuta scheme for u velocity. Similarly, this is going to be the second slope function, third slope function, and the fourth slope function of u velocity. And u0 and u0 and un are going to be the old value and the new values of velocities. Okay, so here's the convention. If you have a k in front, it's going to be a slope function. Okay, if you have the number 1, 2, 3, 4 represents the steps, the Rangikuta steps, the slope function calculated after each and every Rangikuta step. Okay, this u, v or h in the actually denote the variables. Okay, whereas u0, u0 or v0, h0 indicate the old value or the previous time step value of that particular variables, and the suffix value n indicates the newer values of them. Alright, and then we need two time steps. We need some time multipliers for the Rangikuta scheme. I'm going to define them as parameters. First parameter is dt6, which is going to be 1/6 of the time step. Other one is half the time step, so which is dt2. Okay, and then I'm going to bring out the old values. Okay, from the main subroutine, the main program, I'm going to take the instead of using the entire UVH, which is actually 3-dimensional matrix, I don't want them. Let me just take the old values out, considering the time step, and save them in U0, V0, and H0, and then I'm going to call the Rangikuta method. So this is how it goes. So I'm going to call the Rangikuta method. This is the This is the slope function calculation for step 1. So this is RK4 step 1 out of 4. I'm going to give the inputs as U0, V0, and H0, and I'm going to get the outputs. The slope functions KU1, KV1, and KH1. Alright. Similarly, in the second time step, I'm going to pass these, that is U0 plus a slight derivative or a slight slope modification of U0 by taking a small weighted value of KU1, the slope function in the previous step. Okay, and I'm going to get the new slope functions. Similarly, I'm going to call them for the third and fourth time, so completing the 4 steps of RK4 method, and then let's actually do the actual time matching based on RK4. Once we get the 4 slope functions, it's time to evolve them. So this is the final step of time matching. So the new value is actually the old value plus the weighted average of all the slope functions with respect to time. Cool. There you go. And now we got the new values, and it's time to update the main value over here, the main UVW, the main UVH. So that's it. So we get the value for the older time step, and save them in U0, V0, H0. I'm going to call the solve subroutine 4 times with different input values, and we'll get 4 different value slope functions for each and every variable. And then using the slope functions, we calculate the new time step value, and then we're updating the velocities for the new time step, velocities and height for the new time step, and that's it. This way our subroutine is over. This Rangikuta subroutine is over. Alright, and now we are going to do the toughest one. This solve module. This is going to take you a lot of time. So if you want to take a break right now, go and take a break and then come back, because this is going to be pretty much serious. Alright, so let's get started. Now if you look at the output over here, it says if you look at the syntax over here, we are giving the inputs later, and then the outputs come out over here. So we need to write U out, V out, and then H out in that particular order, and then we are going to give a input velocity, which is UN, and then VIN, and then HN. So this is our input U velocity, input V velocity, and input height. These are our slope functions of U, V, and H that is going to come out of the subroutine. Alright, and then as usual we need the use params module, use model vars, because it's going to use them. This is very important. This is the advantage of Fortran, because if you want to include multiple variables, let's say, all you have to do is just include the modules as it is, and this will work just fine, and you don't have to worry about how the variables are being used. And then let's call implicit none. Alright, so let's put intent in and out for these variables. So there we go. So these variables un, vn, and hn are going to come inside with values, so we put int and in, and these variables should not change with time, so we're going to keep it as int and in as it is. The dimensions are 1:nx and 1:ny. So these variables, they're going to they come inside without any value predefined. So we're going to, and they're going to go out with some value. So we're giving int and out, the same sizes for that matter. And then let's create some variables as we go along. So these are the iterating variables i2 and j2. i2 is for the x direction and j2 is for the y direction. Okay, and these are start stop variables. This will be much more evident when we actually write the finite difference schemes. Okay, so right now just follow along with me. I'll explain you about as we go along, and then we'll be using some constant gradient for gradient calculations. For constants during this finite difference schemes, and we might come across these. So this dx20 is going to be half of 1 divided by 2 twice dx, and dy20 is 1 divided by 2 dy, and then gravity multiplier constant nothing but gdx20 and gdy20 is actually gravity times dx20 and gravity times dy20, and then this is actually the diffusion multiplier constants. So it's eta divided by square of dx, and this is not eta, nu, the kinematic viscosity, divided by twice divided by dx square, and this is actually nu divided by the distance along y direction, which is d squared, which is dy times dy. Okay, and now we're going to create some new variables over here. So let me copy this, paste it, and then let me explain. Because right now if you're writing finite difference, your head will start spinning right now because this is a bit messy. Okay, so let's actually take the equations itself, and then you might understand this better. Yeah. So these are the shallow water equations over here. Let me push this to the side. Okay. Okay, fine. So let me push the variables to the side, and then hopefully I can convince you what's happening. Okay, so the advection terms hx, hy, ux, uy, vx, vy are actually these terms. This first dou eta by dou t, these are the tendencies these are the slope functions that we're going to calculate, so these are not the ones. Hx is actually this term, dou by dou x of eta in times u. This is hx. This is the advection term along x component advection term. This is the y component advection term along for the continuity equation. So this is hy. So this is hx. This is hy. And similarly, in that same spirit, ux is actually this term over here, u dou u by dou x, and this v is actually, and this uy is actually v dou u by dou y over here. Okay, and then similarly this is vx and this is vy, and then Coriolis components fu and fv are actually these terms. This is fv. Okay, this is fv and this is fu. All right, and now what we have is that we'll have the gravity of the pressure gradient terms. So this g minus g dou eta by dou x, this is actually our gravity pressure gradient term, gravity of the pressure gradient term, which is gx, and this is our gy, and this bu bv, as you might have understood right now by my notation over here, this is bu and this is bv. As far as ux, these four terms are concerned, these are the viscous terms in the momentum equation. So uxx is actually this term dou square u by dou x square, and uyy is actually this term dou square u by dou y square. And similarly, this is vxx and this is vyy, all multiplied with eta, nu over here. All right. So with that being said, let's actually continue with the let's actually continue with our equations. Strange. Anyway. Alright, so we need two loops first of all, and these constants I'll talk about as we go along with it. So first we need a j loop, loop for y-axis. So j2 will be equal to 1 comma ny and 2, and then we have another loop for the x-axis, so I2, excuse me, nx and 2. Okay, so alright, so first what we're going to do is that we're going to call this indices function. We're going to call this indices function for j2, and we're going to set the values for yb, yc, and yf. Alright, similarly inside this iterating loop, inside this loop, okay, the inner loop, I'm going to call the indices subroutine. I'm going to set the value of xb, xe, and xf. So what do these actually mean? Well, now let's write the subroutine directly, and we'll understand what's happening. So I'm going to call this subroutine over here, and this is indices, which is going to take, let's say, I2, nx, ny, so not ny, this is xb, xc, and then xf. Alright, let me I think this should work. So let's write them out over here. So implicit none. So these two variables are going to come in, these variables are going to go out with the new value. The reason why I write these indices is as follows. Suppose this subroutine is going to simplify our job with writing the periodic boundary conditions, and also it's going to simplify our jobs in writing the index notations. This is as follows. Imagine this case when I2 is 1. The iterating variable I2 is 1. That is, we are on the leftmost edge of the in the domain. And then, so if we go using some kind of a central difference scheme, okay, we need to find the derivative at that edge point. For that, we need a point that is exactly at the back. Likewise, we need a point that is exactly at the center, and we need the point at the forward direction. So in the forward, which is forward direction along x direction, which is actually towards my right, the index is I2, the forward point, the point in front of me would be I2 plus 1. Whereas the point behind me, there wouldn't be any point behind me. So if I were to put a periodic boundary condition, the point exactly behind me will be nx. So this is the point behind me, so that's going to call as xb, or x at the back. And xf is actually the point in front of me in the x direction, so I'm going to call it xf, which is whose value is I2 plus 1. So this xf is going to have the index of the point that is in front of me. Xb is going to have the index notation of the point that is at the back of me, and the xc is going to contain the index that's going to contain my index value. That's it, my present index point value. Okay. Similarly, suppose if the point is at nx, let's say that we are on the rightmost edge of the x-axis, then for central difference purposes, we need a point at the back, the current, and then the forward point. The forward point is actually 1 because we are at the rightmost edge. So if you want the point in front of it, we have to circle around and come back to the point to the leftmost edge. So I'm going to put xf to be 1, whereas the center point is actually I2. Doesn't matter, it's obvious. And likewise for the backward point, since I'm staying at I2, the point behind me is nx I2 minus 1. Simple enough. Okay. And now final thing would be is, what about the interior boundary points? Well, as far as the interior boundary point, that is for I2 which is not greater than 1 and less than nx, I can always find a point that is in front of me and at the back of me without any issue. So if the center point is always I2, the forward point is I2 plus 1, and the backward point is the index of the point that is behind me is I2 minus 1. This entire logic applies to x-axis, y-axis as well. I assume what you call as a doubly periodic boundary condition, and that's what I'm going to do. So if I'm staying at the bottommost edge, if I'm staying at the bottommost edge, let's say the point behind me is actually the point on the top along the y-axis. Okay, the point in front is just one level above. The center point is this. Similarly, if I'm the top, let's say, the point behind me is actually one level below. That's obvious. point, and this is the center point, and this is the point which is actually in front of me. That is nothing but the point at the bottommost. For all the other interior points, the index notations xb, xf, and xe are just the same. Xb is just 1 point behind me and 1 point below me for y, and xf is 1 point. Yf is actually 1 point above me, like that. So hope you understood this, because when we write the finite difference schemes, instead of writing I plus 1 or I minus 1 or something like that, instead of getting confused by that, this notation is going to be a little easy. So with all that being said, let's actually write the continuity equation terms one step closely and step by step. Okay, so how much time is it? It's already 15 minutes into the video. So okay, we are going in a good pace. So let's write the continuity. Let's write the finite difference schemes for the hx and hy terms. So how do I do is as follows. I just take the forward point in x direction, and then I'm keeping the y value constant, y x constant. Okay, because its derivative is about x-axis, so I'm going to keep the y derivative constant. Okay, and then I'm going to multiply this by un, which is the u velocity at again in the forward point, the point in front of me, by keeping the y constant. And then after getting this product, I subtract the same value, but for the point this is slightly behind me about x-axis. So I put xb. I should have put this as I2 plus 1 and j2, and then this is I2 plus 1 and j2, and this one to be I2 minus 1 j2, and then I2 minus 1 and j2, like that. But because of this notation over here, our life is a little more simple, so we don't have to worry about the plus 1 minus 1 conditions and all, because these are already taken care of by the index notation. Okay, this way, and then we have to divide this by twice the distance, twice 2 dx, that is. Since we are already put dx20 as 1 divided by 2 times dx, all you have to do is just multiply this by dx20, and my advection term for the continuity equation is done for. Okay, the hx term is done for. Likewise, if I write this, and if I just keep x constant, and then do the derivative with respect to y by changing the coefficient y, okay, coefficient in the y-axis, I get the derivative for my hy term as well. Very simple. Okay, and dy is, as we mentioned earlier, is the same thing, 1 divided by 2 times dy instead of dx. Other than that, if you look at this, these two equations are done. Now what I want you to do is just take a moment and then maybe try this out in a piece of paper, okay, to convince yourself that this is correct. Okay, yeah, okay, if there is an issue or something, let me know, but most likely I'm pretty sure this is right. Okay, likewise, moving on, now we are ready to write the difference equation, we are ready to write the algebraic equations for the other, numerical equation for the other terms as well. So this is actually our ux term, ux term, so which is u dou u by dou x. So this derivative calculates, this part over here calculates the dou u by dou x derivative along x derivative, similar to how we calculated over here, and this is the u term in front of it. So this is the ux term in x direction, and similarly this is the ux term in the uy term, so which calculates the derivative dou u by dou y about y, and then multiplies that by v in the front. Alright, so with here we calculated ux and uy, done. And similarly, let's continue this and write this equation for vx and vy. Okay, by the way, during this process, if you get confused, just pause the video, write this in a piece of paper, and try to see how this difference equations, how these numerical equations came up, and you will understand this clearly. So this will calculate the advection terms about the y momentum equation. If you look at it, write once, all you have to do is just change the coefficient slightly, and you'll get the terms easily. This part is very simple actually. And then what you have to do is and then let's look at the equations actually. Let me bring the gedit as well. So let's look at them one by one. So this is hx we taken care of it over here. Okay, this is hy, and we're taking care of it over here. Okay, and ux is actually this term u dou u by dou x, which you can clearly see over here. This is dou u by dou x. This is ux. So this is un times the derivative of u with respect to in x direction, which is given by this central difference formula. Okay, similarly this is uy, so that's why you have v velocity in front of it. Okay, and similarly this term is vx, so that's why you have u velocity here, and we're taking the derivative of v velocity with respect to x. And this is vy, so that's why we're taking v velocity here and then derivative with respect to this. Okay, and now what I'm going to do, I think I'm going to keep this as it is. Okay, so that you can cross verify with these terms as I write about the remaining terms. So this term over here, these are our in the FV term in the x momentum equation. There is fairly very simple, just f times b in, and this is our fu term in the y momentum equation, which is f times u in. Fairly simple. Okay, actually one of the simplest in the entire program. And now after this we have to calculate these two terms, which is gx and gy. So let me copy this and paste it over here. So here is how it goes. This h high derivative with respect to time with respect to x is actually this dou eta by dou x, and I'm putting g dx over here because if you look over here, g dx is actually gravity times dx20. So this will take care of the gravity constant multiplication and then the division by twice dx. This term g dx20 takes care of that. Similarly, this term over here takes care of the derivative in this term as well, the gy term, this term in the y momentum equation. Okay, and similarly these two terms, this is fairly simple, just like we saw. This is the viscous term, this viscous drag term Vd that we put in the parameter model, and then this is the Vu term, and this is the Bv term over here, which we calculated. Simple. And then let's write the diffusion momentum equation. This is going to be pretty. This is going to be the largest ones. Bear with me. Okay, this is going to be a little bit confusing. So just be a little careful while you write it. So the central difference scheme for a second derivative like this is the point forward. Okay, the value of the point forward plus the value in the point behind me minus twice the value at the center. Okay, so that's how we go about with this. So the point forward in that direction plus the point behind me, okay, minus twice the point at the center. Okay, and then what you do, you just have to divide this by, and you have to multiply this by kinematic viscosity and divide it by dx dx square. So nu dxx term over here, if you see, nu dxx term is actually kinematic viscosity nu divided by dx square. So similarly this value over here, nu dyy, is actually kinematic viscosity divided by dy twice, dy times dy. So for ux's term, which is nu times dou square u by dou x square, I just have to write this difference scheme and then multiply this by nu dxx, so that's taken, with that it's taken care of. Similarly, I just have to change the coefficient here and write it by nu dyy. Okay, u dyy, and then all I have to do is just copy these two terms and then paste them here, and then I just have to change this u to v, and this equation is done. Okay, and now with this, the finite difference scheme for each and every one of these points is done. Okay, the final thing what you have to do is that to get the slope function, you have to sum up all these terms and go about with it. So the summing up is the most easiest part of it. So let's I'm going to copy and paste these up there. So h out is actually dou h by dou t, which is actually minus of hx plus hy. Okay, and similarly, so if you want to know how this is, there, I needed that snap feature. Anyway, So if you look at this h out, this is actually this term plus this term are taken to the negative side. If you take these two on the negative other side, it becomes negative. So this is h out, which is dou eta by dou t, which is actually minus of hx plus hy. Similarly, if I add these two and subtract this, which is minus of ux plus uy, this will take care of this. Fv is over this term, and gx and gy term are always on the negative side, so they're already in the negative side. So I just have to minus gx and minus bu, and then you add uxx and uyy. This way, my term dou u by dou x is completed. And similarly, if I do the same modification, write them up and sum them up with our corresponding signs, my y momentum equation is done. Thereby, my slope function is complete. There we go. This is our full-fledged finite difference scheme. And now the reason why I wrote this as two different methods is as follows. This solve module is going to be the same, not a problem. But in the future, instead of using Runge-Kutta fourth order scheme, if you want a different scheme like Adam Bashforth or second order Runge-Kutta scheme or something like that, all I have to do is just comment out this module and then write a different time step, and I don't have to worry about the solve module over here, because for different time step methods, the solve module is going to be essentially the same. Okay, just following the same routine I followed earlier. That's about it. Now, with this done, final thing is going to be this saver module. Okay, for this is purely, for saver module, you can use any way to save this. Okay, instead I'm using NetCDF files. You can use any of the other files possible. So I'm not going to force you with that, so I'm going to keep it optional. So what I'm going to do is that I'm just going to copy all of this and paste it over here. If you don't understand any of this, it's perfectly fine. Okay, if you don't understand any of this, it's perfectly fine. So I'm just going to paste them up. This is actually a large file. Okay, what I'm going to do here is I'm just going to call NetCDF module, which is going to be in the libraries, and this is the parameter module that we define, and this is the model variable module. And then I'm just setting the number of dimensions variables over here, and then in net variable placement, NetCDF variable placement ID, and I'm going to create some attributes for x direction, y direction, and the time, and then I'm going to create dimension IDs as such, and I'm going to create some sizes of three-dimensional variables with these two values. This is for three-dimensional variables, and this is for two-dimensional variables. And then I'm going to create the variable names: uname, u velocity, v velocity, height levels, and Coriolis, and then the units. Okay, meter per second, height is meter, Coriolis is 1 by second, and then meters east, meters north. These are just unit names, and then seconds forward, like that. And these are the variable IDs. This is for u. This is the variable ID for u, variable ID for v, variable ID for h, and the variable ID for the Coriolis component f. These are the variable IDs for dimensions x, y, and t. Okay, and here I'm going to create an empty file. This f name is actually given over here. The f name is given over here. Since we are importing the parameter module, this f name will be directly used over here. Used over here. And these are some inbuilt commands that are available in NetCDF to make sure everything is working fine. All right. And then once you create them up, you define the dimensions. You allocate dimension values and try to place them up. So you do that, and then you create the dimension variables, and then you set the attributes, and then you set the dimension IDs. Hold on. Set the dimension IDs, and then create the variables, and then you actually place the variables one after the other. This is actually a pretty lengthy process. Just hold on a second. Okay guys, sorry, I had a phone call in the middle of the night. Anyway, proceeding on. What I was saying is that these will put the attributes inside the files, and here I'm storing and closing all the variable definitions. and then in these lines I'm calling these inbuilt functions to write the variables inside with the variable ID and the corresponding variables, and I close the file over here. And then and then for each and every function, a function call or a subroutine call, and I'm using this check function over here to make sure that everything runs fine. If there is an error, it will throw an error and will stop the entire program. Okay, now you don't have to necessarily know all this, okay, to save this solver module. You can write your own, as I mentioned, you can write your own way to save these variables. I'm just going to use this. I thought of letting you know, so that if you want to try this out, you're very well encouraged to. That's it. So with this, our model is complete, and now what we'll do is that let's create our make file, okay, along with this. So we can close all this. We can minimize this, and then we'll create a make file over here. So let's create an empty document, make file, okay, and then let's open this with gedit. There we go. And then let's increase the size so that you guys can see this clearly. So I already have the make file ready with me, so I'm just going to paste it down. So this is the make file for the model. So I'm going to call the executable as sw.exe. So I'm going to give it a name called as prog. So I'm going to create a variable like that, and then I'm going to create these folders. Remember, we just kept a few folders for the source folder. So I'm going to keep the source folder as vpath, okay, and I'm specifying that as src. The object directory objdir, I'm going to keep this as ops objs, and then the module folder, which is going to contain the module module, which is going to be this mods. I'm going to say this in the variable moddir, and then the executable folder, the one that is going to have the executable file, is going to be this execdir. The folder is exec. All right, and now let's write some compiler flags that we might require. Compiler flags, okay, actually compiler and flags. Okay, it's working. So fc, which is actually a Fortran compiler, is going to be gfortran, okay, and then a few more flags which we'll write it down and then I'll explain. There we go. So this is our Fortran flags. So that's going to give it f flags. So we're going to compile this, and we're going to compile this with the highest level of optimization, O3, and you need this flag as well because the executable is going to create a very large data file. Okay, so if you don't put this flag with medium value in it, the program might run into a segmentation fault and then crash. So you need a large value for it, and then we'll debug it to see if there are any errors to be put. So this -g, and then for the NetCDF library, okay, we need to put this include path over here. So my NetCDF library is installed over here in user include, okay, so I need to input this in. Similarly, this is going to be the linker flag, which will be used when all the object files are combined to create the executable. So I'm going to copy all of these and paste it over here. Okay, the only difference being is that I'm going to put this link flag over here, which is pointing towards this user library, and then with this linker flag lnetcdff. Okay, this is for Fortran, and then finally the linker command is actually the Fortran compiler with this -o flag over here, which is going to link them up. Okay, and then I'm going to copy these down, so this might be of help. Okay, I'll talk about these two in a moment. This one objs, this is the variable that's going to represent all the object files. So the object files are initializer, sw_rk4, main.o, saver.o, and parameters.o. Okay, these are the object files. So when we write this line, okay, so when we write this line, instead of GCM I can even write model. Let's say model. Okay, I'm going to create this program file, program executable, and then let's write the compilation steps and a little bit of notifier steps. So these are the notifier steps. So this creates the model. So prog is a equal for the dependency, for the requirement prog, the dependencies are the object files. So when to create the executable, we need to have all the object files created, and they'll tell about how the object, when all the object files are ready, we're going to create the object file using this particular line. So it's going to call the Fortran flag, the G Fortran -o, and then it's going to put the object file, say executable. It takes all the object files and then links them up using this linker flag over here. Okay, and then after doing all this, it's going to move all the object files to the object directory. It's going to move all the module files into the module directory, and then it's going to move all the executable files into the executable directory. And to get all these done, we need to specify how to compile all these Fortran, get all these object files. So that's fairly simple. Where if for a corresponding object file, we need a corresponding Fortran 95 file to be ready. Okay, so the command we do over here is as follows: Fortran compiler, and then you put flags, Fortran flags. Okay, and then we put this line over here. This makes sure that each file will be taken one after the other. This will point to the first file in the not the first file. I think I can remove this. We don't need these two, honestly. Anyway, this will take one file at a time and start working on with them. And with that, this part is ready. What we finally need is we need something to clean them up, and so we're going to write these lines over here. This is for the make clean option. So these echo statements are going to tell us what's going to print out these lines during the compilation to make it a little more fancier. And this clean will do what it does is that it's going to remove all the tilde files, temporary files, NetCDF files, plot images, executable object files, and all. And similarly, it's going to go inside these particular folders and remove all of these. All right. And then finally, to finish this make file, we need the dependency chains. So let's write the dependency chains over here. So there we go. The params module, the params.o file needs this file parameters.f95. Params, I would say. Is it? How did this work? Okay, I think it's parameters. Okay, this is parameters.o. Okay, to get this parameters.o, we need this file definitely. For all the other files, we need the corresponding F95 files and the parameters.o files to be compiled and ready. And this way, our make file is complete, and we have make file is complete. There we go. This way, our make file is complete, and now we're ready to rumble. Actually, ready. So let's close this up, and then let's open up a terminal. Okay, and let me increase the size of this, zoom in a little more. I think this should be good enough. So make sure we're in the same path, and now to compile this, it's just easy. Just type make model, that will compile everything. So this will take the object files. Clearly you can see there is actually an error. Fatal error. It's not a GNU Fortran module. That's odd. That's odd. I thought this should work. Hold on, I'll just pause and kind of rectify this and come back. Hello everyone, welcome back. Actually, there was a small mistake. Make file. Thing is, I have multiple versions of G Fortran installed in my computer, so I just have to specify exactly which compiler I'm going to use. Earlier the error came because it tried to use some other compiler that was available. So what I did is in the make file, I just specified the path of the G Fortran compiler that I would like to use. That is actually the system G Fortran. Okay, so then the error went away. So here we go. Where's that? Yeah, I think we can minimize this. Okay, so now if I type if I look at this, it's over here. Now if I type make clean up everything up, and we type make, there we go, the compilation is done, and we also have the object file compiled. So if you look at this ls, it looks like there is nothing. So but if you go to exec file, there's executable sw.exe. Let's come out, then let's go to objs. There are the object files neatly arranged, and then if you go to src, there are our files, source files. There we go. And then if you go to our mods, there are our module files. There we go. Sweet. And now with this done, let's actually run the executables. So to run it, it's fairly simple. Just type exec, okay, and then there's a sw.exe. Now you run this. There we go. It started, and it started all the calculations, and it's going on fine. Now we finished all the calculations, okay, and now it's taking time to save up all the data. It's placed all the variables, placed all the distance variables and time variables, and now it's placing up all the bigger ones, the u variable. Hopefully in a few more seconds this should finish. That's v. I think we have 2 more to go. And there we go, done. And now if you look at list it out, you will see that there is a file called as data_small rotation, okay, there, and that file is ready. Now let's keep this as it is, and now let's go to the source file, okay. Where is that folder? Yeah, here what I'm going to do, I'm going to the source file. I'm going to open this parameter file again, okay, and now instead of small rotation, we just have something like large rotation, and then this omega, I'm going to keep it significant, so I'm going to increase this by a factor of 4 orders in magnitude, making it really significant, okay. And now I'm going to let's close this. We don't need this anymore. Where is that terminal? Yeah, this one. I'm going to clean the module up, okay. Now it's created the new file, and now now let's run this model again. This one will take care of will run the model for a higher value of rotation, and then it's going to save this in a new file called as datas_large rotation, okay. Once this is done, we can actually go and look into the data and then analyze it ourselves. So just have to wait for a 2 minutes, I guess. Three more variables left. Yeah, there we go. And now we can actually close this, minimize this up, and now we can actually look into these variables, data files. Each of these data files are it's 2.4 gigabytes in size. They're actually pretty big. And now what we need is a Python file to look into this. So let's open and create a new Python file. See, I'm using Python file. You can use anything for that matter. I'm going to call this visualize.py, and I'm going to open this with gedit. Zoom the screen up for you, and I'm going to paste this code over here. Okay, if you so this helps, it helps to know a little bit of Python here. I'm opening up this my NetCDF file using Python, and I'm going to plot it. I'm going to give a simulation as to how this looks like. So first what I'm going to do is I'm going to show this in a 2-dimensional field, the height variables. So I have this NetCDF module available in Python installed in my laptop, so I can call this, and using this I can open up all the variables. So this is the file name that I'm going to open up. Okay, I extract these variables out. Okay, and afterwards I can do a bit of a diagnostics myself. So for now I'm just going to open up the empty figure, and then I'm going to plot all the variables. Okay, going to give a video simulation of how this looks like. So let's open up my terminal. Okay, I don't need this. Clear this up. I have a visualize file over here, so I'm going to use my Python file. Now I'm going to visualize this. This will take a bit of time, and after reading you should be able to get a video, right? Not a video, a plot about now. There we go. This is for small rotation case. Okay, let me zoom this up. So what exactly happened here is that we put a drop. Okay, the water level went down a bit, and then it's going to go up and down. This is going to cause a lot of ripples, and these ripples are going to propagate with space in all the directions. So you can see the clear wave motions happening. What's happening here is that we have the nice ripple action happening, and the waves are actually moving towards it, the boundaries. And now since this is a doubly periodic boundary condition, so waves that go over here towards my right, they'll emerge from left, and the waves that go towards my left emerge from the right. Similarly on the top and bottom. And now you can clearly see that the waves are actually interfering with each other, and they're going to cause a lot of interesting wave phenomena. Okay, since it's a doubly periodic boundary condition, you can clearly see that the overall spatial solution is quite symmetric, quite symmetric, axisymmetric. So all I need is just one. How do I put it? All I need is just one quadrant to analyze the data, and everywhere else is going to be the same. This is actually the wave motion, actually the ripples on top of the surface. Okay, clearly you can see this. It's all messed up, and it's interacting in a different manner. Okay, and this is going to go on till 1000 seconds. Clearly you can see a lot of ups and down motions. So wherever it is red, it means that the water level or the liquid level is higher than the mean, and wherever it is blue, it just says that the water level is slightly lesser. Fluid level is slightly lesser, like that. Yeah, I think you'll get this. Okay. Now what I can do is I can just keep it as it is, and you can see it for yourself till the end of the video. So now actually I'm going to cancel this simulation. Okay, cancel the simulation and open up this file for this other one, the large rotation. The first case, the rotation did not cause much of a difference, and now it's going to cause a significant difference in the results. So let's look at the large rotation file. This should take a little time as well to open up, and there we go. Now because as you go up and down, there will be a large Coriolis effect. The wave solution actually, instead of spreading evenly in all the directions, it just starts confined within a slight boundary, slightly north and south. So instead of having a nice wave, so you'll get to see a clear wave motion over here. So you can see this is one wave. Most likely this is going to be called as a Kelvin wave, and this one is most likely the Rossby wave. Correct me if I'm wrong. So these waves are actually moving towards in each other direction, and this wave comes towards the other end because of the boundary condition. And now you can clearly see that these two waves will interact with each other, and they're going to form quite a lot of interesting dynamic features as a consequently. And now you see these two waves are interacting with each other. Okay, and a lot of interesting features start forming as a consequence. Now you have what you call as a complex wave interaction phenomena, and you clearly see whatever be the case. Okay, it does not go beyond a particular in the y direction. These interactions do not go beyond particular value in the up and down. That's the reason is because of the Coriolis effect. As you go towards up, the Coriolis effect increases in magnitude and in the positive sense, so the so the wave motions is actually pushed towards your right, and as you go down, the Coriolis deflection pushes the wave motion towards your left, and as a consequence they become they are aligned towards x direction. So a meridional motion or a vertical motion, that is, how do I say, a y direction motion is actually confined. So these waves are technically trapped within the center. In the context of Earth, they call this as something similar to what you call as an equatorial trapping, wherein waves that are produced at the equator are confined to the equator because of the rotation of the planet. Okay, so that's your two examples of your case studies. Now similarly, I can actually go on and on with it. And now I can actually go and change the parameters inside and play around with it and do a lot more fancy stuff. So if you're interested with this, you can actually go and play that, do that yourself. Now what I'm going to do, I'm going to set this to small rotation again, and I'm going to comment out these lines. Instead of commenting, comment out these codes, and then I'm going to uncomment these lines, uncomment, and let's see, should I leave this as it is? Okay, I need this one. Uncomment the code. Now get ready for an actual 3D, actual two-dimensional simulation. Okay, I'm going to take the height variable again. Okay, and now watch this. Lights, camera, and action. Now you will be able to see the actual perturbation. Hold on. Yeah, you see now there's a big indentation in the center. Okay, that's because of the initial condition we give. And now as time progresses, now what you'll notice is that this indentation, the bump we gave in the center, is going to come up, and as it comes up, it's going to go up and down and up and down and up and down, and this is going to create a wave motion that's going to spread out in all directions. Clearly you can see this is the upward motion because of the dent, and this is going to cause a wave that is going to spread in all the directions. I know this is, the simulation is a bit slow because I gave a smaller stride step, but nevertheless, clearly you can see it's going up. It will go up, and after some time, you'll see this watch after reaching a maxima, it starts going down again. The center peak over here. I think right now it reached its maxima, I suppose. I think it started to flatten. Let's see. Now this ridge over here, this is actually a surface ripple because of the motion of the fluid. People actually call this as the surface gravity wave, or the gravitational wave. That in astrophysics and cosmophysics, this is actually the gravity wave. Okay, so and now it starts going down. It starts to go in. It's going to cause the next round of waves as a consequently. And now these waves, as they go towards the edges, they're going to come out and through the other sides because of the doubly periodic boundary condition, and they'll start interfering. Hold on a second. And now as they approach the surface edges, you can clearly see, the surface edge of the surface itself, they start bending. They start deforming. Now you can clearly see here it started deforming. It started deforming over here. Even here, you can see the deformation happening very obviously. And now, as these come over here, you're going to notice something even more interesting. The complex wave interactions and interference and constructive interference, all of that is going to happen now. Actually, this is pretty interesting. I just keep my fingers crossed so that to see something interesting over here. Ready?
and now this surface starts to increase in deform, and is increasing in height, indicating this wave went out and is going to come here. Similarly, this wave also started increasing, indicating another incoming wave. You clearly see this part mellow down, and it's mellow down and indicating that a wave is actually moving forward. There you go. Neat, huh? So this, now what you can see is that the same kind of a wave motion will start happening in the y direction in this direction as well, and as we move along with time, this is going to continue, and a lot of wave activity will happen over here. This is close to this is our solution for one particular case of shallow water equations. And now with this model you have in hand, now you can actually go and tweak this model and do different kinds of simulations as you like. Now what I'm going to do is that now I'm not going to wait till this entire interactions happen. Okay, I'm just going to stop this video over here. Hope you guys understood something interesting out of this, and hope you guys are able to come up to all this point. With this kind of a framework, you can write your own models from now on. Alright, so that's all I have for you guys in this video. Thank you for watching, and I'll see you guys next time in another interesting video. Till then, take care. It's Aaron.